In this exercise, we want to determine the current Y of t through this 2 Henry inductor. We have a 3 amp source. At t equals 0, this switch moves from here to here and connects the 3 amp source to our inductor. So, since we need the results for t greater than 0, let's go ahead and redraw the circuit for t greater than 0 just to make sure that this switch doesn't confuse us. So, take a look at the problem and see what we expect. We have one energy storage element. It's an inductor, so this corresponds to an RL circuit. So we have one inductor and some number of resistors. We have a constant input, so the form of the solution is going to be y of t is some constant k1 e to the minus t over tau plus k2. Now we just need to find k1, tau, and k2. For an RL circuit, we know that tau is equal to L over Req. So let's find an equivalent resistance seen by the inductor. So kill our source. Current source becomes an open circuit. 2 ohms, 6 ohms. These are the terminals that we want a voltage-current relationship across. And here's 3 ohms. This has infinite resistance, so an infinite resistance in series with 2 ohms is an infinite resistance, so no current goes through this leg here. So any current going this direction will also go through this resistor, so those two are in series, so Req is 6 ohms plus 3 ohms, or 9 ohms, and tau is equal to 2 over 9 seconds. Now let's find our initial condition. Initial conditions are always determined by invoking the fact that inductor currents can't change instantly and capacitor voltages can't change instantly. So we're going to look at the circuit just before this switch has moved. So at t equals 0 minus, the circuit looks like this. 3 amp source, that's shorted across this switch. This goes to a 2 ohm resistor. This goes to a 6 ohm resistor. If the switch has been in this position for a long time, everything will become constant, and this inductor will look like a short circuit, and this is 3 ohms. So this current is Y at 0 minus, which, since there's no source connected to it, is just going to be 0 amps. If I use this expression here, as t goes to 0, e to the minus t becomes 1, so this becomes k1 plus k2. This is one equation in 2 unknowns that we can eventually use to solve for k1 and k2. Final conditions. So these are set up as t goes to infinity. We have the 3 amp current source connected through a 2 ohm resistor with a 6 ohm resistor. Again, as t goes to infinity, with this input being a constant, the inductor is going to look like a short circuit. Here's our other 3 ohm resistor, and this is Y at infinity. So this is just a current divider. So Y of infinity is going to be the total current, 3 amps, times the resistance in the other leg, 6 ohms, over the sum of the two resistances, 6 ohms plus 3 ohms, which is going to be 2/3 of 3, which is just 2 amps. Now if I evaluate this as t goes to infinity, e to the minus t goes to 0, so this expression just becomes k2. K2 is equal to 2 amps. If I plug that on up here, k1 is negative 2 amps. Now all I need to do is plug the various numbers into this equation to get my final solution. I don't need my drawing anymore, so I'll get rid of that. So plugging in my numbers, y of t is just going to be k1, which is negative 2. E to the minus t over tau. 1 over tau is 9 over 2, so this is e to the minus 9t over 2, plus k2, which is positive 2 amps. And this solution is correct for t greater than 0.